Problem number 12. A delta connected resistive load is connected across a balanced three-phase supply of 400 volt. Find the symmetrical components of line currents and the delta currents. Okay, so find the symmetrical components of line currents and delta currents. So line currents are denoted by small suffixes. Delta currents or phase currents are denoted by capital suffixes. I capital A, I capital B and I capital C. Okay. So now they had given the delta connected three-phase resistive load. So for ABC sequence, A, then B, then C. Okay. So these nodes I have taken as A, B and C. Okay. So this diagram is given along with the question. 15 ohm is the resistance, 15 ohm in one phase, 20 ohms in another phase, 250 ohms in the other phase. Okay. And they had given the load is connected across a balanced three-phase supply. So the values of all the three-phase loads are different. So the load is not a balanced one, but the supply is a balanced supply given the voltage is 400 volt. So unless it is specified, consider this 400 volt as the line voltage. So what is this 400 volt? It is the voltage between A and B, or voltage between A and C, or the voltage between B and C. What is it? It's only the magnitude. So now we are going to write in terms of the phase angle. Okay. So balanced supply, magnitude 400 volt. So you know, for a balanced system, the magnitude will remain the same and the phase angle will differ by 120 degree following an ABC sequence as shown in this diagram. Okay. So we can write, by considering VA as a reference vector, V capital A is equal to 400 angle 0. V capital A is equal to 400 angle 0, line voltage. Okay. And V capital B is 400 angle minus 120 degree or plus 240 degree. Okay. So see, VB is behind VA by 120 degree, or it is ahead of VA by 240 degree. We can write in either ways. VC is 400 at an angle 120 degree or at an angle minus 240 degree. Okay. So it is ahead, VC is ahead of VA by 120 or it is behind VA by 240. Either 1 plus 120 or minus 240. So in a delta connected system, we know phase voltage will be equal to the line voltage. Okay. So now I have redrawn the delta connected system. Given system I have redrawn and I have used the same terminals. Okay. So for the line currents, I have taken I small a, I small b and I small c. Okay. And the vertices are marked A, B, C. Okay. And we have taken I capital A as current, I small b, c. You can refer the delta connected derivation. I capital A is equal to the current flowing through the phase BC. So we have taken the current through the phase BC as I capital A because this phase is opposite to vertex A. In the same way, the current which flows through phase C to A is taken as I capital B, which is opposite to vertex B. The current which is flowing from A to B is taken as I capital C because the phase AB is opposite to vertex C. Okay. So now I capital A, I capital B and I capital C are the phase currents. Okay. And you know, in the case of a delta connected system, line current and phase current will be equal. So the voltage across A and B lines is nothing but, V capital C. Okay. So since it is IC, it is V capital C. So how we can consider it as V capital C? Because again it is opposite to vertex C. Similarly, opposite to vertex A, V capital A. Okay. So the voltage across the lines B and C is taken as V capital A. The voltage across the line C and A is taken as V capital B. So in accordance with that, we have marked the impedances 15 ohm as ZB as it is opposite to B, 20 ohm as capital ZC and 250 ohm as capital ZA. Okay. So now we know the impedance or the resistance for each phase and we have the voltage across each phase. Okay. So using those two values, we can find out the current through each phase. That is, the phase currents can be calculated. So the phase current I capital A is equal to V capital A divided by Z capital A, which is 400 angle 0 by 250, which is 1.6 amperes. In the same way, calculate I capital B as V capital B divided by ZB. What is V capital B? Which is 400 angle 240 divided by 15. 400 angle 240 divided by 15. Okay, which is 26.67 angle 240. And I capital C is equal to V capital C by ZC, which is equal to 400 angle 120 by 20. You will get as 20 angle 120 degree amperes. Now let's calculate the symmetrical components of phase currents. Okay. So I capital A naught is the zero sequence component of phase current. 1 by 3 IA plus IB plus IC. Substitute and you will get the answer as minus 7.25 minus J 1.93 amperes. So the positive sequence component of phase current I capital A1 is 1 by 3 into IA plus AIB plus A square IC. Now you know what to be substituted for IA and what to be substituted for A square. You will get the answer as 16.1 amperes. The negative sequence component I capital A2 is equal to 1 by 3 into I capital A square IB plus AIC. Substitute, get the answer is minus 7.25 plus J 1.93 amperes. So I capital A naught, capital A1, I capital A2 will give you the symmetrical components of phase currents. Okay. So now symmetrical component of line currents are IA naught is equal to 0. Okay. So when we have already proved it from the derivation, or if you want you can check. Okay. So IA1, I small a1, the positive sequence component of line current IA1 is equal to J root 3 I capital A1. So J root 3 into 16.1, get the answer. The negative sequence component of line current I small a2 is equal to minus J root 3 I capital A2. Substitute, get the answer as 13 angle 75 degree. Okay, remember capital suffixes phase current, small suffixes line current. Coming to problem number 13. A balanced star connected load takes 30 amperes from a balanced 3-phase 4-wire supply. So 3-phase 4-wire means it is a star connected system. If the fuses in two lines are removed, find the symmetrical components of the line current before and after the fuses are removed. You are asked to calculate the symmetrical components of line currents, small suffixes, before and after the fuses are removed. So first let us solve for before fuse removal. So before fuse removal, what are the three line currents? IA, IB, I small c. They are given. It is a balanced load, balanced supply. So magnitude is given. Considering IA as the reference, we can write the other two currents. IA is 30 angle 0, IB 30 angle 240, IC is 30 angle 120. So now the zero sequence symmetrical component of line current IA naught. Write down the formula. Answer will be obtained as 0 amperes. IA1 is 1 by 3 IA plus AIB plus A square IC. Substitute, get the answer, which is 30 ampere. And IA2 is 1 by 3 into IA plus A square IB plus AIC. Substitute for all the parameters and get the answer, which is 0 ampere. Okay, so this is the values for symmetrical components of line currents before the fuse removal. Okay, so the second part is after the fuses are removed. So in two lines the fuses are getting removed. Okay, so let us say the two lines in which we are removing the fuses are lines B and C. So when fuses are removed or blowing out, there is no continuity. The two lines become open and IB becomes 0, IC becomes 0. Okay. So IA will be 30 angle 0. IB and IC are 0. Okay. So now the symmetrical components of line currents after fuse removal. Use the same formulae. IA naught is 1 by 3 IA plus IB plus IC. You will get as 10 ampere. IA1 is 10 ampere and IA2 is also 10 amperes. Okay. So coming to the problem number 14. For a grounded three-phase generator, the three sequence voltages are EA1, EA2, EA0. Okay. So notice this, for a grounded three-phase generator. If the ground is removed, okay, and the terminal of phase A is grounded, determine the new sequence voltages. Determine the new sequence voltages. Okay. So here we are going to represent EA0, EA1, EA2 as the sequence voltages with neutral grounded. Neutral of the three-phase generator grounded. So after the ground is removed from the neutral point, instead of neutral grounding, they are grounding phase A. They have asked to calculate the new set of sequence voltages. So the new set of sequence voltages, we are considering it as VA0, VA1, VA2. Okay. So what is EA0, EA1, EA2? The neutral of the generator grounded. What is VA0, VA1 and VA2? Neutral ground removed and phase A terminal is grounded. Okay. So by removing the neutral ground and grounding the terminal A, the diagram is drawn like this. So let us take EA, EB, EC as the EMFs induced in the three phases. Okay. We have considered star connected because they had given for a grounded three-phase generator. That means neutral point should be there for grounding. Okay. So when the terminal A is grounded, what is VA will be equal to 0. Okay. VA will be equal to 0. Okay. So ground is removed, then the terminal A is grounded. Okay. So we can write VB equal to EB minus EA. Okay. So you apply this KVL for this. Okay. So what is VB? It is the voltage between these two terminals. Okay. So this here there is no ground. So now it is like plus minus minus plus. Okay. So it is VB with respect to B terminal we are finding. So apply KVL for this loop and you will get VB is nothing but EB minus EA, plus minus minus plus. Okay. Similarly, VC is between C and A. For this two you apply KVL. Then you can write VC is equal to EC minus EA. Okay. So now write the usual formula. VA naught is equal to 1 by 3 VA plus VB plus VC. What is VA? 0. What is VB? EB minus EA. What is VC? EC minus EA. Okay. Expand it. EB minus EB plus EC minus 2A. Okay. So we wanted the answer to be in terms of EA0, EA1 and EA2. So we are doing some alteration over here. So minus 2EA is taken as minus 3EA plus EA. Okay. So after replacing minus 2 by minus 3 plus 1, what we are doing is we are taking this EA and grouping along with this EB plus EC. So this EA plus EB plus EC, one term, minus 3 EA. Okay. So which is 1 by 3 into EA plus EB plus EC minus 1 by 3 into 3 EA. So what is this 1 by 3 into EA plus EB plus EC? It is the zero sequence component of EA. Okay. So 1 by 3 into EA plus EB plus EC is nothing but EA naught. Okay. Minus EA. So we will get VA naught is equal to EA naught minus EA. So zero sequence component with A grounded is equal to zero sequence component with neutral grounded minus EA. In the same way, write the formula for VA1. What is VA1? Zero sequence component with A grounded is equal to 1 by 3 VA plus AVB plus A square VC. Substitute for VB and VC. Expand it. So you will get 4 terms. Group the positive terms AEB plus A square EC and group the negative terms EA, AEA and A square EA. Okay. So again I told you we need it in terms of the positive sequence component before removing the neutral ground. Okay. So to get in that term, we are doing some substitution over here. We are putting minus EA plus EA. Okay. And this plus EA you group to this positive terms, minus EA you join with this negative terms. So when you group like that, EA plus AEB plus A square EC minus EA into 1 plus A square. We all know 1 plus A square is equal to 0. So VA1 is equal to 1 by 3 into EA plus AEB plus A square EC. What is this? 1 by 3 into this term? It is nothing but the positive sequence component EA1. So the positive sequence component with A grounded is equal to positive sequence component with neutral grounded. So VA2 formula, write the formula, substitute for VB, substitute for VC. Expand it. Again you will get 2 positive terms and 2 negative terms. We are doing this adjustment over here. Minus EA plus CA. Plus EA group with these 2 positive terms. Minus EA group with these 2 negative terms. Okay. Now group all the 3 positive terms. Group all the 3 negative terms. You will get minus EA into 1 plus A square, which is 0. This term is 0. So what is 1 by 3 into EA plus A square EB plus AEC? It is the negative sequence component EA2. Okay. So what we got? We got VA2 is equal to EA2. Okay. So negative sequence component with A grounded is equal to the negative sequence component with neutral grounded.